Okay, hello and welcome back to another Transport 2 video. So in this example, we have a spherical shell. So something like this. And there's a uniform thermal conductivity. So K is uniform or constant throughout this example. And there's an inner radius of 1 meter, so that would be here. This is Ri. And then at this point here, this is the temperature. And then we have another radius of 2 meters. So that would be all the way out here. And this is the outer radius, and then that would be the temperature of that outer. And we are trying to find the temperature at the radius of 1.5, so that's somewhere in between here, or at the midpoint of these two. And we can say let's call it M for the midpoint. So we can use Fourier's law for this example, like we talked about in the last videos. So that is going to be that the heat flux is equal to the negative thermal conductivity times the area times the change in temperature over the change in position. And this whole example is going to be at steady state. So we can say that this whole thing is equal to some constant C. So now let's plug in that the area is 4 pi r squared. So now we have that the heat flux is equal to negative thermal conductivity times 4 pi and the radius squared times the change in temperature over the change in position. And this part here is a separable differential equation. Okay, so now we can rewrite this part as negative the integral of dt from temperature at 1 and the temperature of the outer is equal to the heat flux over thermal conductivity times 4 pi, because this whole section is going to be constant, and then we're going to take the integral of 1 over r squared of the change in position, and this is from the radius 1 to the outer radius. And I can rewrite the Fourier's law because the change in position is really the change in the lengths of the radius. And then we can integrate both sides. So this will be negative temperature of the outer minus the temperature of the inner. This section is going to be constant still. And then it will be 1 over the radius initial minus the radius of the outer. And then because of this negative sign here, this will flip. So we can just rewrite it like that. So then let's look at the values from before so we can plug these in. So we had that the inner radius is 1 meter. The outer radius is 2 meters. And this temperature at the outer surface is 0 degrees Celsius. The temperature at the inner surface was 100 degrees Celsius. And we're trying to find what the temperature is at the midpoint at the radius of 1.5 meters. So let's plug these values in. So we have 100 degrees Celsius minus the initial, which was 0 degrees Celsius, is equal to the heat flux over K thermal conductivity times 4 pi. And this is going to be 1 over the inner radius of 1 meter minus 1 over the outer radius, which was 2 meters. So this gives us that 100 is equal to the heat flux times thermal conductivity of 4 pi times 1/2. So this will be 200 Then we can multiply the 4 over as well. So therefore we have that the heat flux is 800 times the thermal conductivity times pi. So now that we know what the heat flux is, we can solve for the temperature at the midpoint. So we're going to be using this same equation from before. We're doing another separable differential equation, but this time we're evaluating it to the midpoint for both of these. So this is going to be temperature initial minus temperature at the midpoint is equal to the heat flux over the thermal conductivity times 4 pi. This is 1 over the inner radius minus 1 over the radius at the midpoint. So let's plug some values in again. So we have temperature initial is 100 degrees Celsius. We're trying to find the temperature at the midpoint. And we know that the heat flux is 800 times the thermal conductivity times pi. This is over thermal conductivity times 4 pi. And then the inner radius was 1 meter. And the outer radius was 1.5 meters. So then here we can cancel those values, and this is going to be 200. This is still like so. And then this is simplifying to 1/3. So now this, we can subtract the 100 over. This is 200 over 3 minus 100. If you wanted to have a common denominator, it's going to be 300 over 3. So when we subtract, this is going to be negative 100 over 3, and then the negatives cancel. So at the end of this, we have that the temperature at the midpoint is 100 over 3 degrees Celsius.